In this outcome, we get to grips with the mole, the chemist's way of counting atoms by weighing them. We'll work with relative masses, the mole's equation, and the concentration of solutions. Let's dive in. Here's the ground we'll cover. We'll define the mole and the Avogadro constant, and learn to use relative atomic mass, AR, and relative molecular mass, MR. Then we'll put the equation moles equals mass divided by MR to work and extend it to concentration equals moles divided by volume for solutions. Throughout, the real skill is rearranging these equations to find whatever's missing and keeping your units straight. Let's start with why the mole exists at all. Atoms and molecules are far too small to count out one by one, and even the tiniest speck of a substance contains an astronomical number of particles. What we need is a unit that ties the mass we can weigh on a balance to the number of particles present. That's exactly what the mole does. It lets us weigh out a known number of particles, which makes reacting amounts predictable and measurable. Relative atomic mass, written AR, compares the mass of an atom to carbon-12, our agreed standard. It's an average mass for the element's atoms, and that average takes account of the natural mixture of isotopes. Because it's a ratio, one mass against another, it has no units. So for hydrogen, AR is 1.0. For carbon, it's 12.0. And for oxygen, 16.0. And you simply read these values straight off the periodic table. Relative molecular mass, MR, is just the sum of the AR values of every atom in the formula. You add up every atom shown, remembering to account for the subscripts. For ionic compounds, we tend to call it the relative formula mass, but the idea is identical. Like AR, it has no units. So for water, that's 2 hydrogens at 1.0 plus 1 oxygen at 16.0, giving 18.0. And for carbon dioxide, 12.0 plus 2 lots of 16.0, which comes to 44.0. Let's fix the terms. Relative atomic mass, AR, is the average mass of an atom compared with carbon-12, and it has no units. Relative molecular mass, MR, is the sum of the AR values of all the atoms in a molecule. Relative formula mass is exactly the same idea, just the name we use for ionic compounds. And isotopes, remember, are atoms of an element with the same number of protons but different numbers of neutrons. Let's calculate a relative formula mass using calcium carbonate, formula C, ACO3. First, count the atoms, 1 calcium, 1 carbon, and 3 oxygens. Now multiply each relative atomic mass by how many there are. Calcium is 1 times 40.1, so 40.1. Carbon is 1 times 12.0, so 12.0. Oxygen is 3 times 16.0, which is 48.0. Add them together, 40.1 plus 12.0 plus 48.0, and you get a relative formula mass of 100.1, with no units. So, what exactly is a mole? It's the unit for amount of substance, and 1 mole is the amount that contains the Avogadro number of particles. Those particles might be atoms, molecules, ions, or even electrons. The lovely thing is that the mass of 1 mole, in grams, is numerically equal to the AR, or MR. So 1 mole of water has a mass of 18.0 grams, and we give amount of substance the symbol N. That Avogadro number deserves a slide of its own. 1 mole contains 6.02 times 10 to the power 23 particles, an almost unimaginably large number, and we call it the Avogadro constant, symbol Na. Its units are per mole. It's the bridge between the number of particles and the number of moles. The number of particles equals the moles multiplied by 6.02 times 10 to the power 23. Think of it as counting in a very, very big dozen. A quick round of definitions. A mole is the amount of substance containing 6.02 times 10 to the power 23 particles. The Avogadro constant, Na, is the number of particles per mole. That same 6.02 times 10 to the power 23. Amount of substance, symbol N, is the quantity we measure in moles. And molar mass is the mass of 1 mole of a substance, in grams per mole. Let's count some molecules. How many water molecules are in 2.0 moles of water? We use number of particles equals moles times the Avogadro constant. Substituting in, that's 2.0 times 6.02 times 10 to the power 23. Multiply the front numbers, 2.0 times 6.02 gives 12.04, and we keep the power of 10, so 12.04 times 10 to the power 23. Tidied into standard form, that's 1.20 times 10 to the power 24 water molecules to 3 significant figures. Now the central equation of this whole outcome. Moles link mass and relative mass together. Moles equals mass divided by mR, or divided by AR if you're dealing with an element. In symbols, N equals mass over mR. 2 things to watch. The mass must be in grams, and the answer, N, comes out in moles. Get comfortable with this one, because almost everything else builds on it. This equation has 3 forms, and you'll need all of them. As it stands, N equals mass divided by mR, rearranged, mass equals N times mR, and mR equals mass divided by N. The easy way to pick the right one is the triangle trick. Cover up the quantity you want, and the layout that's left is your formula. So if you're after mass, you multiply N by mR. If you're after moles, you divide mass by mR. Let's find moles from a mass. How many moles are in 36.0 grams of water? Given mR is 18.0, we choose N equals mass divided by mR. Check the mass is in grams, and 36.0 grams, yes it is. Substitute in N equals 36.0 divided by 18.0. Carry out the division, and 36.0 divided by 18.0 is exactly 2.0. So we have 2.0 moles of water. Now the reverse, finding a mass from moles. What's the mass of 0.25 moles of sodium chloride, given sodium is 23.0 and chlorine 35.5? First work out the mR of sodium chloride, 23.0 plus 35.5, which is 58.5. Now use the rearranged form, mass equals N times mR. Substitute, mass equals 0.25 times 58.5. That multiplication gives 14.625, which we round to 14.6 grams to 3 significant figures. Let's check your understanding. First, state the value and units of the Avogadro constant. Second, calculate the mR of sulfuric acid, H2SO4, with hydrogen 1.0, sulfur 32.1, and oxygen 16.0. Third, how many moles are in 88.0 grams of carbon dioxide, mR 44.0? And fourth, rearrange N equals mass over mR to make mass the subject. Give those a go. Let's move on to solutions and concentration. Concentration tells us how much solute is dissolved in a given amount of solution by comparing the moles of solute to the volume. In words, concentration equals moles divided by volume, and in symbols, C equals N over V. There's one unit trapped to flag now. The volume must be in cubic decimeters, dm cubed, which gives concentration in moles per dm cubed. Let's nail those volume units because this trips people up constantly. Concentration needs the volume in dm cubed, not cubic centimeters. Now 1 dm cubed is 1,000 cubic centimeters, which is just 1 liter. So to convert cubic centimeters to dm cubed, you divide by 1,000. For example, 250 cubic centimeters becomes 250 divided by 1,000, which is 0.250 dam cubed. Always sort your units out before you substitute anything in. The concentration equation also comes in three forms. As written, C equals N divided by V. Rearranged, N equals C times V, and V equals N divided by C. To keep them straight, remember what each stands for. C is the concentration in moles per dm cubed, N is the amount of solute in moles, and V is the volume of solution in dm cubed. As before, cover the unknown to reveal the layout you need. Let's calculate a concentration. We dissolve 0.50 moles of sodium hydroxide to make 2.0 dm cubed of solution. We use C equals N divided by V. Check the units. N is 0.50 moles and V is 2.0 dm cubed. Both fine. Substitute in C equals 0.50 divided by 2.0. The division gives 0.25, so the concentration is 0.25 moles per dm cubed. Now let's find moles from a concentration and volume. How many moles of solute are in 250 cubic centimeters of a 0.100 moles per dm cubed solution? First, convert the volume. 250 cubic centimeters divided by 1,000 is 0.250 dm cubed. Then choose N equals C times V. Substitute in N equals 0.100 times 0.250. That multiplication gives 0.025, so there are 0.025 moles of solute. Here's one that combines two equations. What mass of sodium hydroxide is needed to make 250 cubic centimeters of a 0.200 moles per dm cubed solution given Mr is 40.0? Convert the volume first. 250 cubic centimeters is 0.250 d minutes cubed. Now find the moles of solute. N equals C times V. So 0.200 times 0.250, which is 0.0500 moles. Then switch to mass equals N times Mr. That's 0.0500 times 40.0, giving 2.00 grams of sodium hydroxide. Let me flag the classic mistakes so you can sidestep them. Using cubic centimeters instead of dm cubed in concentration sums is the big one. Forgetting the subscripts when totting up an Mr is another. Then there's confusing Ar for atoms with Mr for molecules. Multiplying when you should divide, or the reverse. Dropping or misplacing the units in your answer. And finally, not pausing to check whether your answer is even a sensible size. Another check for you. First, convert 500 cubic centimeters into dm cubed. Second, find the concentration of 0.10 moles dissolved in 0.50 dm cubed. Third, find the mass of 2.0 moles of calcium carbonate, Mr 100.1. And fourth, what mass of sodium chloride makes 1.0 dm cubed of a 0.50 moles per dm cubed solution, Mr 58.5? Work them through carefully. Let's pull the outcome together. Ar and Mr are ratios you read from the periodic table. 1 mole always contains 6.02 times 10 to the power 23 particles. The equation N equals mass divided by Mr links mass and moles, while C equals N divided by V links moles, concentration and volume. Always convert cubic centimeters to dm cubed before using that concentration equation. And with practice, you can rearrange either equation to find any missing quantity.